In the last video, we introduced the concept of center of mass, and what we want to do is try to extend that idea that we found in the last video to describe a continuous object. Because in the last video, we were finding the x-coordinate of the center of mass of a bunch of point masses. But now, what happens when we want to describe and find the center of mass of a continuous object like this rod up here? So this is a 2-meter long rod. It's a super thin metal rod that has constant density, and we want to find the x-coordinate of the center of mass of it. But in the last video, we found this. So we took each x position, and that x position got some mass associated with it. That's how that x position was weighted. And we had all those point masses to do that with. So at each x position, we were able to weight that with the mass of the point mass, and we were able to sum those up and divide by the total amount of masses. But now, looking at this rod here, we don't have any point masses to grapple with. We don't have anything to hold on here. We have this continuous solid object. So how do we find a center of mass of this continuous object? Well, what we need to see is, rather than having these point masses here, these m sub i's, we're actually going to split up. We're going to chop up this rod into a bunch of mass pieces. So we're going to split them up into these even pieces, and these are going to be called delta m. And what we're going to do now is replace all of these m sub i's in our sums down here with delta m. So these are now going to become delta m. Now, what we want to do is wonder, okay, what happens now when we take the limit as delta m goes to 0? What happens when we get super small pieces of mass? So the limit as delta m goes to 0, and the limit as delta m goes to 0, what do we get? Well, we're going to end up with some integrals now. So we're going to have the definite integral. Let's make that neater. We have the definite integral, and when we talk about this rod here, we're going to describe the length of it. But right now, let's just keep it general. So we'll go from a to b, and our integrand is going to be x. And now we said that delta m is going to 0. So delta m going to 0 is now going to give us dm. So that's what we have there. And then we're going to divide by the definite integral from a to b of dm. And really, this isn't anything different. We just have new tools now to help us calculate the center of mass of continuous objects. But really, these integrals are doing exactly what we were doing in the last video. It's just saying that, okay, we're going to go to an x position, and we're going to, at that x position, it's going to be weighted by some chunk of mass. And you're going to continue to sum up these positions weighted with the mass at that position, and sum all those up, and then you're going to divide by the total mass. That's what this bottom integral is just the total mass of our object. And that's exactly what we saw in the last video. But now we can work with the center of mass with continuous objects, which is wonderful. And really, the last little ingredient that we need now is, okay, what is dm? What is dm? That's what we need to find. And when I introduced this rod to you, I said it had a constant density. It was a uniform rod. It has a constant density. So in order to talk about dm, we need to first talk about density. And this guy right here is lambda. And lambda describes linear mass density. So linear mass density. And if you're like me, when you're introduced density, you're told it's mass over volume, which is certainly true. But in this context here, when we have different units, we have mass. Linear mass density is defined as mass over length. So still describing density, we have different units here. We have a different object that we're looking at. So this in units, we could maybe say that this is kilograms over meters. We could say something like that, kilograms over meters. This is linear mass density. And we said that it's constant, but we still need to connect this up to dm. So what we're going to say is that lambda is equal to a tiny change in mass, so change in mass over a change in x. And now we're interested in the limit as these get super small. So as these get super small, lambda is now going to be dm over dx. And then we can solve for dm. Multiplying both sides by dx, we're going to have dm is going to be equal to lambda dx. So now we just solved for dm, and now we can substitute that in. And let's apply this, actually. Let's do this. So we want to find the center of mass of this rod over here, this 2 meter long, super thin rod. And let's fill in what we have. So x bar is going to be equal to the definite integral from 0 to 2 now, 0 to 2. And then x, we have x. And then we just found dm. And dm we said was lambda times dx. All right? And now we're going to be dividing by, let me grab a little more space, dividing by this definite integral from 0 to 2 of dm, which we said was lambda dx. And again, this integral in the denominator is just the total mass of our rod. That's all it's saying. So let's calculate these. And I said lambda was a constant, so we can pull it out. That is totally legal. So we have lambda times definite integral 0 to 2 of x dx. All right. And then we have down here, lambda, we can pull out again, definite integral 0 to 2 dx. And lambdas will cancel. And I need to say this because in the next video, we're going to have a density function. And in the next video, we definitely cannot pull out lambda when we actually have a density function. So we can only pull out lambda in this scenario because we were told that this is a uniform rod and it has a constant density. So we're treating lambda as a constant here, but it won't always be. So just remember that. Now let's finish this off. So we have x squared over 2 evaluated at 0 and 2. And then over we have x evaluated at 0 and 2 as well. And this comes out to what? We have 4 over 2, so that's going to be 2. And then in this denominator, looks like just 2. So we're left with 1 meter. And that's exactly what we expected. And you could see this in real life too if you were to go grab something that had some uniform density to it and you were to figure out where you need to put your finger in order to balance it on your finger. And in this case here, we found that to be 1 meter, which is exactly what we expected. And in the next video, we're going to work with a non-constant density function.